All right. Well, thank you very much for the intro, Zhao, and thanks for organizing everybody. Welcome to another great adventure in ARIA and related projects from our collaborators. Models of reality is another name for digital twins. And what I want to start with is really, well, where did Zhao just finish, which is the potential for digital twins is pretty obvious if you're from certain backgrounds in graphics or asset creation. But I want to provide a slightly broader frame of reference that, as Zhao ended on, connects quite a lot of the research topics that are going on at CVPR now. And interestingly, the history of CVPR is rooted in embodied computer vision, more so than sort of like the modern era of internet scale photo analysis. And so we've got a great coming together of the topics, and certainly the digital twin, models of reality, maps, is one of the things that really has joined us over the ages of computer vision research. And as we look at this picture of Earth, I want you to think about how many models of reality are actually going on today that you utilize and interact with, be it the weather systems, the transportation tracking systems that make sure that your UPS and FedEx get wherever they need to, etc. These are all different models of reality that utilize maps of actual reality overlaying physical reality. And the thing is, of course, we're in the moment of Gen AI, where the potential for what it means to generate samples of possible realities is very exciting for people, very exciting within asset creation. But there's something perhaps more profound about the potential of a map of our actual physical reality, which is really what I want to talk about today. What if we were to build a digital twin of our entire actual physical reality? So I'm going to start by asking this question: what do we want our maps, models, digital twins to represent? And certainly I'm a great utilizer of things like Google Maps and related products. It allows us every single day to know where we're going, what's actually around us. And that's because effort has been put into building that kind of digital twin. Zooming a bit closer, again from Google, not so many years ago now, we started to see this incredible shift in understanding that we could transport ourselves to parts of the planet and experience kind of being there with Street View and other related technologies. And this is incredible because before that, you really either did have to have a friend there that would send you a photograph, be it on the internet, or you had to travel there. Whereas now we can think about traveling, via this digital twin. I mean, step into my apartment. I can promise you it's not as tidy as this one. But we start to see the things where we're actually used today, the fact that this is not a photograph at all, but is in fact a rendering from a catalog produced from digital twins. Every single thing in there is in fact a digital object which has its textures and its various lighting structures and is rendered. Get a bit closer in and we see something that has utility like this sink. And if we think about the digital twin as like the hundreds of thousands of items that may be in a person's apartment and ask like what would be important for whether it's an AI assistant or a robot that's helping you there, we step under the sink and we see a common item in North America, which is the incinerator. And this is a garbage disposal unit, which when they break down, you need to know what's inside if you want to fix it. And so we can start to ask, how functional can our digital twins become? How far into the functionality can we get? And how can we do that with computer vision techniques? I mean, by the way, the answer may be not at all. This may be outside that realm. But all the same, these are digital twins. And if you want to fix it, you're going to need to understand these parts, not just in the abstract. It's not just a bolt. It's a particular bolt with a part number that needs a particular amount of torque on it. Otherwise, you will break the incinerator in exactly the wrong place and then have a much heftier bill. So we're used to the fact that this here, is it a rendering? Is it a photograph? Of course, it's a rendering. Can have digital assets associated with it. And we're trying to invert the process of getting basically these digital assets, absolutely everything, down to every single nut and bolt on the planet. Now, that's an audacious goal, but in a nutshell, it says, what if there were a digital twin catalog for everything in reality? Every single chair in this room, every single room in this conference hall, every single conference hall in the city, and on. Well, you'd have to have these three parts to make them useful for all of the applications. You need the physical form, which itself can, of course, have not just the surfaces and the textures, but articulations and other functionalities. what happens when you interact with it. You can link that to meta information about those digital twins, about the physical objects, for example, information about how to fix a thing that probably exists on the internet. And the important thing is that the linking of that digital twin to the ability to effectively detect what it is and say, I can re-identify that thing, that's a critical part of a digital twin as well. So not just what it looks like so that it can be used in, for example, a game engine or in a video, etc., or for training a generative AI model, but actually to identify that this is this particular chair in our actual reality. Okay. Now I want to zoom straight over to a completely different kind of model of reality so we can contrast it, which is a human level model of reality. I want to understand what is it that we as humans actually need to represent for our own model of reality. And given it's still early in the morning, I'm going to warm up with a experiment here. So we're about to see a waiting room created for a science experiment on human visual attention from Cohen's lab. It's going to look like this. We ought to pay extreme attention to what's going on. Look as hard as you can. Look around and see if you can spot anything odd in the room over the next 20 seconds. Okay. Anybody got any idea what just changed, if anything, in that room at the back? A picture? What about the picture? I guess there's a human first. Anybody else spot that? One other person. Anybody else see anything interesting change? Shout it out. The rug's missing. Okay. Rug's missing. Anyone else see that the rug is now missing? Okay, let's have a look at this. Yeah, that was the start. That was the last frame. First frame, last frame, back and forth. As you watch that 20-second video with great intent, with the owner task, check what's going on, that's what was changing. Now, what can be going on here? What's this digital twin? What's going on in your mind that seems to not be able to see and detect and see the changes that are happening? Well, that's the difference between effectively what your human brain needs in its everyday reality and this task that actually we perhaps think would be pretty trivial for a machine, AI assessment or a robot with computer vision to understand. What does it actually tell us about our experience of reality and about what might need to be in a digital twin? Plus, effectively, we were, using these models of reality. Okay, here's another example. Hopefully everybody here can see two intertwined spirals. Between the pink is a green and a blue one. No one disagree with that. What are the colors of the red boxes? Fix it in your mind. Let's have a look. Yes, indeed. Of course, they're absolutely the same color. Otherwise, why would I show you this illusion? What's going on is that, again, whilst our digital twins might want to be calibrated in color so that under lighting conditions, we can relight them correctly, actually, from a human perception point of view, you really are not seeing absolute color values. There's relative things going on. It's relative to the lighting in this room. It's relative to the contrast of colors. It's relative to your particular human vision system. So our concept of authentic and accurate digital twins that are necessary, for example, for understanding what's going on in reality from a human perspective may be very different than we understand what may be possible, for example, in graphics applications. And it gets even more interesting. Here's Simon Green here showing his thumb to demonstrate the fact that it actually only has high resolution within the 2-degree field of view, which is about your thumbnail at arm's distance. So if you stick your thumb out at arm's distance and you can see it in your field of view, would you believe it that actually it's only within that field of view that you have high resolution where, for example, you can read text? Everything else is extremely blurred. How blurred? Well, in fact, this is a demonstration from Project Aria where we simulate actually with not even any like as extreme change in the resolution between the fovea as a person reads this book and the rest of the field of view. Now, how can this be? You look around you and it all looks like it's in high resolution. And if you have full color vision, it looks like it's in full color. So what do we need for a digital twin when this is all we see? We don't see in full resolution everywhere. We don't see in full color everywhere. And we don't even detect changes when they're happening. So what do we need in our digital twin? Okay, one last thing to convince you of how weird it really gets when we contrast human perception and what we may be looking at. This is Michael Gersler. My only instruction to him, he leads one of our research teams, is to look in the mirror and move his eyes backwards and forwards and look at himself doing that. And hopefully everyone here can agree that he is indeed moving his eyes backwards and forwards. Okay, this is what I was asking him. I said, Michael, can you confirm that you are moving your eyes backwards and forwards? And he says, I can confirm that I cannot see my eyes moving backwards and forwards. How is it possible that Michael cannot see his eyes moving backwards and forwards? The answer is, again, what it is that humans actually see is not what you think they see. What happens during your eye movement is effectively you're blind, especially to high resolution changes. So when you're looking at your pupils from a distance, even this close up, you're not actually able to see your eyes moving, because as you move your eyes, the speed at which you move them would blur the underlying representation on the back of your retina. So your vision system is evolved to say, I will simply ignore that information because I can't do anything with it. So let's put this all together. Now, given that you move your eyes, you can test yourself, throughout this day, you'll find yourself moving your eyes quite a lot, maybe 8 times a second. During those eye movements, which does take time to move your eyes, you're not seeing anything. When you do see it, it's within just a partial 2-degree field of view at any kind of high resolution. And anyway, even if you're intently looking for changes everywhere, you can't detect them. So what is going on in a human's mind is very different from what we might think of when we think about how complete a digital twin of reality can be. Okay, so digital twins and models of reality. We need to know for the application space what needs to be in a model of reality. For a robot or an AI, it may be very different than for a graphics application. Once we understand that, how do we build such a model of reality? And I think importantly, for most of our sort of modern research, how do we keep models of reality up to date? Now, I want to claim that we should do at least one thing here, which is to aim for superhuman models of our reality. And there's a few things here. Superhuman, contrast that with the experiments we've just done that obviously shows that if we aim for human level models of reality, it may be very incomplete. And our reality, not just any reality, a model of our actual world that we're in is going to be extremely useful. And before I kick off and get us through this overview of how we're building this, I want to show you one experiment with Project Aria that we've been doing at Reality Labs. This is 4 or 5 Project Aria devices that are world locked using the SLAM system into the single frame of reference of the actual world, which allows us to understand where those devices are relative to each other and effectively share any information that is observed between the different devices. And I want to show this to convince you that the future we're heading into is one where actually you can think of these new devices like Project Aria and the products that were built on top of the technologies from it actually allow us to say, instead of a device having to continuously detect and infer what's going on, so much of our reality, in fact, is shared together. Think of us in this room. How much compute even needs to go on in any single device, especially if another device has already been there, or if somebody else is already looking over there and their device has already understood what's happening there. This is a profound insight that we can share. It's superhuman because, of course, we can't telepathically talk to each other and infer what's around the corner, not unless you're on the phone, whereas our devices can talk to each other. And so you can think about this potential for a model of reality which is kept up to date in real time by our devices. Now, we've been calling that live maps, a live updating model of reality, a virtual copy of our dynamic world kept in sync with our actual world. We think this is an audacious goal for scientists and product designers of our age. If we build such an asset for humanity, it will be profoundly useful. Now, understanding all of this is spatial AI. So we're going to dip into that now. The workforce of spatial AI in our team, and of course a lot of our partners, is Project Aria. And this is a V1 device that got released in 2020. James will be coming up later today to talk about the Generation 2, which is extremely exciting. Generation 1 introduced a lot of computer vision sensors that had never been put together into a single package like glasses, But what it's allowed us to do is to develop the foundational technologies of 6-degree of freedom location. So this is the visual inertial odometry stack, the SLAM or simultaneous localization mapping stack, and the visual inertial bundle adjustment stacks that basically allow us to get a device to know where it is in the actual world to very high accuracy. And not just for one device to know where it is, but for it to know where it is relative to other devices consistently in the same time and over time. Now, just so you've had a chance to see these barcodes, I'm putting them up because so much of everything I'm about to talk about is based on effectively technologies that are available to everybody here today through the project area, research community, and the machine perception tools. So do take a photo of that. First of all, I'm going to talk about non-parametric models of reality built with Project Area. To kick us off, actually, some work from Zhao Yang and team demonstrated, and this is a project that's online now, that with a single Project Area device, when you do have that capability of SLAM from Project Area, then you can start to do things which we're used to seeing, like Gaussian splat reconstructions. But if you've ever tried to produce a Gaussian splat or a NERF or any other kind of photometric reconstruction from video data, let alone video data that doesn't have stabilization of the camera device, you'll find that you'll run into a lot of different problems. Now, one of the main problems, in fact, independent of the quality of the output of the reconstruction, is the fact that video data has trajectories, when they're running into thousands of frames, that if you try and estimate the pose alone, you'll end up using something like ColMap. And that may take apparently on the order of 4 days to run if it doesn't crash completely. So anybody who's had experience trying to run like large-scale Gaussian splats up there using a NERF Studio and so on will know that this is a major problem. Because we've solved the location problem, we can now start to look at reconstructions that can be done using Gaussian splat technologies in 20 minutes, because effectively the visual positioning system is providing a very good initialization for where the camera is. So that means that reconstructions like this can be got from a single area device simply walking around. That's very exciting. And it certainly starts to point out like the quality that might be possible for digital twins using devices that look just like glasses. Now, 20 minutes isn't real time, and so the team has been pushing on exactly how do you start to get real-time reconstructions of Gaussian splats. And some of the work from Wu et al., which is certainly inspired and following the pioneering work that MonoGS actually showed only, I think, last year, and got the best demo award, that indeed this is a fast-moving field. It's very exciting to be in essentially the causal estimation space for things like photometric models. There's a lot of details in building systems like this. Underpinning it, of course, is being able to have real-time location and otherwise being able to manage the data volumes that can really start to grow. So you can't keep all of that raw video data and, for example, do a stochastic gradient descent step on all of it at once. You have to manage it. Now, back in 2015, 10 whole years ago, I had the privilege of winning the Best Paper Award here for dynamic fusion. This was back in the day when we still had depth cameras that were in use. And it's interesting to say, well, here's a real-time dynamic reconstruction of reality. How are we doing in getting, to this kind of quality and beyond, but potentially not using depth cameras that are, certainly expensive from a power point of view, even cannot go onto a pair of glasses. And it's actually kind of incredible to see this field moving on. As Zhao just pointed out, some of the work from Zhu et al. Demonstrates the potential for how using just monocular video from ARIA, you can train a feed-forward only neural network to directly output 4D Gaussians. This is like a Gaussian splat, where it has temporal dynamics. And instead of using an optimization framework, instead what we've got is where the network directly infers the four-dimensional space-time volume of Gaussians. Definitely worth checking that work out. Okay, they're non-parametric. What does it mean? Well, it means that there was no distinction there between anything in the world. We started this talk looking at the potential to decompose all the way down to the nut and the bolt. But what we've just seen are effectively space-time videos. Certainly very useful and a substrate for machine perception in the future. That is to say, that space-time video really should be thought of as the data volume on which all computer vision could be based. But parametric models give us another opportunity, both in sparsifying an understanding of reality and also setting us up to start to say, could we do better even than those non-parametric reconstructions if only we know something about what's in reality? So here what you can see is, again, a single project area device as somebody walks around their apartment. And what we're doing here is inferring using something like Mass2 format, but many other effectively, 2D-based CNNs are appropriate, and then simply triangulate that back into bounding boxes. It's actually, kind of easy now to think about how to put a system like this together when you have a project area device with its location known and technologies like Mass2 format. Now, having this kind of model of reality is already very useful. Obviously, having your building outline and knowing where things are, is super useful. We'll get on to what else we can do with that now that we know where the walls are and what objects are in space. But I don't want us to, just look at static reality. I want us to get back straight into understanding that humans are the agents of change. If anything is going to change in reality, it's because humans are changing it. That's another profound thing to think about. The only way that all of the chairs got into this room today is probably one at a time, or maybe a few at a time, by people moving them. And so as we start to understand the potential of wearables, tracking the state of change of reality over time as it changes, what we end up with is an understanding that there's so little things changing in reality that actually the problem becomes much easier. So if you start off with a baseline of a model of reality and saying what's changing now, well, if you're actually at the point where the humans are changing it, it becomes much easier. What you see here is, in fact, the state-of-the-art work that's coming out of a new part of our team where we're looking at inferring entire body models, again, just using single project area devices. I recommend looking at the HMD2 work and also the Ego LM work from Ling Ma and team that's at CVPR this year. This is where we use a diffusion model to take the live head pose and the things like clip embeddings and the point cloud that come from ARIA, and being able to say that we can understand exactly what the entire body is doing. And we can do it not just for the wearer, but we're starting to look at how we can do it for bystanders in the space. Because these are all part of a functional digital twin of reality. Now, I'm showing this because not only is it incredibly exciting, this is, by the way, a Project ARIA Gen 2 device that you can see in operation here, where we're inferring the bystanders. Again, it's about triangulating inferences that come from 2D back into 3D because we have the pose of the single camera and all of its sensors. It's important to look at this because as we venture into this world of real-time digital twins, it's going to be vital that we're able to do things like preserve privacy of bystanders. So by being able to detect where people are, you can do things like say, actually, do I even have ownership over those pixels? I could just literally delete them so that the AI cannot even look at it, even if they're being sent over to a server to stream for VLMs, for example. But of course, beyond that, having the state of bystanders, especially if they're collaborators, friends, family, is very, very exciting. So this is all part of a digital twin. When you put those things together, you start to get a system that looks like this. A human interacting in their reality from a project area device. And here we're introducing the fact that here we see them interacting with the world. So we can update that model, that simple bounding box model in real time, just by looking at where it is that they are interacting. And we can do that using things like hand tracking technology. Again, that's available actually the new 21 key point tracker on Project ARIA. Okay, so we've got these bounding boxes, but surely we're in this digital twin workshop. We can do a lot better than that. Well, again, the same project from Xiaoyang and team that demonstrated entire scenes being reconstructed can be applied to reconstruct just high quality models of single objects. And if you can detect those objects, you can zap them back into the model. So this is actually another example of 3D Gaussian splats once you've really understood how to calibrate and bundle adjust the cameras in Project ARIA. But of course, next door, we have our friends looking at 3D and other generative AI applications, and these worlds are coming together. So here I just shamelessly grabbed a set of links from Yao, one of our researchers in London, that says, well, hang on a second, if we are able to capture big libraries of models, we can pre-train models to have massive priors on what the world looks like, and then we can do things like text to 3D. Do I even need to sort of know the pixels here? Can I simply say that this is a Coke can and instantiate a Coke can into my 3D digital twin? And the answer is yes, that is what's starting to happen. But of course, if what you want is your actual, chair, your actual apartment and things, you're going to need to condition it on your pixels. So this is where some of the work is coming in, where that's exactly what we do. We take pre-trained models, these large reconstruction models, and we say, can we improve on the state of the art? And in fact, that's where we're starting to see some real hope. Massive pre-trained models that enable conditioning based on the data that comes from, for example, point clouds or pixels from wearable devices can start to instantiate very high quality 3D assets. And some of that other work, in fact, here's another example. Is it a photo? Is it a model? Of course, they're all models, right? That's always going to be the case throughout this entire workshop, hopefully. What you've got here is where it builds on top of those LRMs and introduces techniques for how to incrementally add data into LRMs so they can improve to fill out where there's basically missing parts of the model, again, from things like wearable devices. Enabling these to become more functional, that is, say, articulations, not just relatable static objects, is really where the cutting edge of this problem space is today. Okay, so live maps, a digital twin of our actual reality, will unlock superhuman perception and spatial reasoning capabilities for all applications. We have no doubt about that. And I think, if you're sitting here starting your PhD, or if you're in the middle of it wondering whether or not you should be jumping ship to the Gen AI space, I think, hopefully you can be convinced that it's not one or the other. These worlds are very much coming together. But in the space of wearable devices, the ability to think about your actual model of reality and being part of this audacious goal of science building a digital twin of our actual planet, kept up to date down to the nut and bolt level, is actually within our grasp. Now, with that, I'll simply leave us with the fact that if you get a chance to see some of our other talks today, please do so. I hope that you get to see the Aria Gen 2 introduction videos to show you what is going to be possible. In fact, it's right after this talk. That's going to be very exciting to see. And with that, I'll thank you.
Thanks for the great coverage. Turn on the mic.
Yeah, so we do have 5 minutes for the audience to ask questions. If you have any questions, please speak in front of the mic.
Yep.
Who will be the brave soul? Oh, there he is.
Great, thank you very much. Just come in front of the mic. Yeah.
Richard, you talked at the very beginning a lot about ways in which humans are not forming the perfect model of reality, and I found that to be super interesting. But then very quickly you started talking about how we want actually a superhuman version of reality, a model of reality. In what ways do you think it's still relevant to consider the limitations of human perception? Especially, what would you consider that a vital part of thinking about how to build the superhuman model of reality, or is there another version of reality or model of reality that we should be building as well?
Yeah, thanks. That's great question. So I put that in there partly because I got to say I'm fascinated by that topic, and it's only the advent of the techniques like Zhao and team have been pioneering that says, well, actually, maybe we can build live maps and it actually be sort of like a full game engine over reality, sort of a vision that we've had for a while. But when we step back and say, but what are the applications? Well, that's when you meet and confront again either a platform that's going to be using that data and the people using that platform, for example, a human. So when we think about rendering a digital twin for the purpose of things that we call social teleportation, the question is what needs to be rendered to the human? Now, in things like Quest devices and Apple Vision Pro, it's already very common, and it's actually standard in all of these devices to do foveated rendering. And that's to reduce the amount of data that's being computed on a device. And that's exactly to match the foveated vision of humans, because you don't need to render all the pixels where they literally cannot see at high resolution. So all of these reduce into practice again, and you should use them wherever they are. Now, the other area, which is not in this workshop, but was in a workshop we did yesterday and later on today in agents and AI, where we look at is say, well, actually, if you've got an AI assistant, of course, it really doesn't care about like the pixels that are being rendered mostly. It cares about the functionality. And from a point of view of understanding what may be necessary for an AI assistant, it's mostly sort of a distillation of that data back into forms that are actionable. So if you're fixing the garbage disposal unit, you kind of don't need to see a full 3D model all the time. I need to know the action I should take right now. And so the point is, though, if you have such models, of course, you can start to train such systems. And you can do it in simulation, and you can do it in ways that, for example, are otherwise, impossible So I think that the key there is to say, well, if we aim for superhuman capable models, there is a lot of applications that distill that data down again. It's kind of the maximalist approach, but certainly it's going to be useful for things that are far more efficient.
Yes, thank you.
Thank you.
Hi, Richard. Really inspiring vision on like just, capturing, recreating and understanding the live physical world. One interesting observation from some of the, human limitations that you highlighted is that the amount of information you need to understand the world could be a lot smaller than the amount of information you need to re-render and recreate the world, right?
Right. Yeah.
And do you see differences in the approaches if you focused mostly on just understanding versus recreation, given potentially orders of magnitude difference? Or do you feel like just going the maximalist, get everything you need for both, because clearly the understanding problem is a subset of the information you need for recreation?
Yeah, this is a really key insight that you're talking about. The answer is almost certainly that we should not worry about having different techniques whilst we need it. But, insofar as it's always easier to do the easy thing, the audacious thing of something like a scientific asset for all of humanity, a digital twin, and a catalog of everything that's going on with permission sharing is just a very different view on what may be possible. So actually, let me just bring up some slide from yesterday, if it's possible here. The trade-off that you're talking about is very real. I'm not sure if this will render on here. Let's see. Yeah, exactly. So if you've got effectively applications in high immersivity, trying to interface the full bandwidth of humans through their sensors. So, what we see, remember, is that experiment. So what we see is not exactly what we think we see, but it's certainly a lot more than just, a chair is a bounding box, for example. You can contrast that with the fact that whilst you can envisage something like a holodeck that really might need, full physical rendering of assets, at least where you're interacting with them, with all-day wearable contextual AI technology and what may be necessary there. And there you can think about Iron Man, Stark glasses. Like, what does that actually need? And do we need like the same assets for both of these? Well, the answer is, whilst we might look at this North Star, the reality is that, in fact, there's always a trade-off between these two, both in the value of the assets and the technologies. Why would I want to walk around in a giant headset that could render pixels, at photorealistic levels and need those assets to be capable of that, when all I want to know is, where did I leave my keys? These are very different problems. And certainly if I want to be able to have that answered, I want to have a device that I can take with me wherever I go. So I don't want to trade off on the weight, etc. And we see that today. So today's smart glasses versus today's mixed reality HMDs. It's not because, product designers can't envisage the potential for something like, Kingsman glasses that can render pixels and be really smart. It's that these trade-offs are about how you can physically really enact those different application spaces. So yeah, when we look at the fact that there are already thousands of orders of magnitude that we have to try and reduce into practice when we're going through the research programs to build products that actually ship, I don't think we should worry about trying to build like a unified thing anytime soon. What I want us to do is to keep in mind that we shouldn't ignore the fact that a complete digital twin of reality would really be like a scientific enterprise that has value far beyond like one application.
So it's like the grand human.
That's right. You got it. What if we were audacious enough to have a grand project for humanity that captured and kept up to date a digital twin? The application spaces are actually quite endless, obviously. It's why the entire industry 4.0 of digital twins, built as designed, etc., is important in those spaces. It just hasn't come all the way down yet to the point where actually that technology could possibly be used to help us in our everyday lives. But if we could, things would change and we would certainly utilize that technology. Yeah, it's a great question. Thank you.
Right. Okay.